Hi, welcome back. In this video, we're going to look at the relationship between the graph of the absolute value function and the graph of its derivative. As you know, as you've already seen, the absolute value function is not differentiable everywhere. So the domain of the absolute value function is all real numbers, but it's only differentiable on the real numbers that are not equal to 0. So everywhere except at x equals 0. So what we found using the definition of the derivative, because there's no other way to do it, what we found was that f prime of x is equal to -1 for all negative real numbers, for all x less than 0, and f prime of x is equal to +1 for all x greater than 0. So before we graph the derivative, let's graph the function. F of x equals the absolute value of x. We know it looks like this. It's a V. It has a point, a corner. And if we look at any negative number, for example, -3, what we found was the derivative at all negative real numbers, the derivative was -1. So what that means is at any negative number, say -3, the tangent line goes through that point and it has slope -1. So it has to look like that. It has to be y equals -x. So we can see that the tangent line coincides with the absolute value function on that at that point. And so if we do that at any negative number, it's going to look the same. It's going to be the same tangent line. And if we pick a positive number, say x equals +2, we found that the derivative at all the positive numbers is +1. So the tangent line has to go through that point, and it has to have slope +1, so it looks like that. It also coincides with the graph of the absolute value function. So it sort of intuitively doesn't look like what we thought tangent lines were supposed to look like. But this is the definition of the tangent line. It's the line that goes through the point and has a certain slope, namely it has to be the derivative of the function at that point. And so that's what it looks like for the absolute value function. So what does the graph of the derivative look like? So let's graph f prime of x just below f of x, the graph of f of x. So for all negative numbers, the graph is going to be a horizontal line, or a half of a horizontal line, y equals -1. And for positive numbers, it's going to be the line y equals +1. So it looks like this. It's got two pieces. And notice it's not defined at x equals 0. So we have two rays pointing, in opposite directions. One of them is the ray y equals -1. The other one's the ray y equals +1. And notice we don't have a point at x equals 0. That's because we don't have a derivative there. What do we call that point where we don't have a derivative? Notice it's a sharp corner. That is called a cusp. A cusp, a cusp is a sharp corner where the derivative doesn't exist. And it's because there's an abrupt change from the derivatives on the right side and the derivatives on the left side. Those derivatives coming from opposite directions are not going to agree. They're going to kind of bump into each other and disagree. So there's a sharp corner there called a cusp. Notice that the absolute value function is continuous everywhere. That means it's defined everywhere. You never lift up your pencil to draw the graph of the absolute value function. That's continuous.
I didn't get that. Could you try again?
And so the absolute value function is continuous everywhere, but it's not differentiable everywhere. So intuitively, graphically, when you have a point where it's not differentiable, the graph may be continuous there, but something abrupt happens. There's a sharp corner. And so notice the graph of f is continuous, but there's a sharp corner there. So it's not smooth. So think of continuity as meaning you never have to lift up your pencil, and differentiability meaning it's nice and smooth and round and not sharp, no sharp corners. That's graphically what a differentiable function looks like. All right, I need to feed my cat, and I'll see you in some other video.